This video is about another diode AC circuit application, which are clumpers and clippers. Okay, so last video we have discussed the first AC diode application, which are rectifiers. Okay, so this time we will be discussing two types of AC circuits, diode AC circuits. They are clippers and clumpers. Okay, let's start with clippers. Clippers, they are also called limiter circuit. Okay, so other names for clippers are limiter circuits. So from the name itself, clippers, clip. Okay, so they have the ability to clip off. So what do we mean by clip off? So to remove, okay? So they have the ability to remove a portion of the input signal without distorting the remaining part of the alternating waveform. Okay, so why do we want to remove a portion of an input signal? So sometimes when we send input signals, or we transmit informations, sometimes there are unwanted signals that are included in the transmitted signal. So, for example, there's a noise in the signal. So, we wanted to remove that, but we do not want to remove the entire signal because the message is there within the signal itself. So, what we want is just a portion of it to be removed. Just a small part of it that we wanted to remove. So what we do is we make use of a clipper circuit. Okay? So there are two types of clipper circuit. We have a series or parallel clipper circuit. So it depends on how the diode is connected to the load. So when the diode is in series with the load, we call that a series clipper. And when the diode is in parallel with the load, we call that a parallel clipper. Also, we can categorize clippers as positive and negative clippers. So if we remove a portion of the positive half cycle of your signal, we call that as a positive clipper. And if we remove a negative or a portion of the negative half of your signal, we call it a negative clipper. Okay, so how do we analyze series diode clippers? So this is an example of a series diode clipper. So as you can see, this looks familiar, right? So this is just like the half wave rectifier circuit that we have. Why half wave? So during positive half cycle, we have plus and minus IV here. So the positive is connected at the diode and the negative is grounded. So positive here with the anode here, that makes your diode forward bias. And since this is forward bias, what happens is we have an output waveform. So during the negative half cycle, this will be reversed. So the negative will be connected to the anode, which will make your diode reverse bias. And in this case, if that is open, we don't have any output voltage here. So at this case, we have a half-wave rectifier. If we remember, so during positive half, okay, so during positive half, you have an output waveform. During the negative half, it is open, so you have a negative half wave, zero at the output, and then you have another half wave here, and then zero. So from the original signal, which is like this, technically, you have removed the entire half cycle. So the entire half cycle here was removed, was clipped off. So therefore, we can consider this as a clipper circuit because we remove a certain portion. Okay? So, for a series diode clipper, the diode is usually in series with your load resistance. So, the diode clips or remove any voltage that does not forward bias it. Okay? So, how do we know that the voltage will not forward bias your diode? First, if you have a reverse biasing polarity, so it happened when when your input signal here reverses, so it become minus and plus, so that means it reverse bias the diode. So once this is open, automatically, since this is a series circuit, no current will flow across your load resistance. Okay, and also, even though we have here plus and minus, if this is positive and this is the anode, but a forward biasing polarity, which is less than zero point 0.7 for silicon or zero point 0.3 for germanium, will still clip off. Okay, so will still make this circuit an open circuit. So therefore, it is not just that that it is plus and anode. It must also satisfy the condition that your input voltage is also greater than zero point 0.7 if it is silicon, and it is greater than zero point 0.3 if it is germanium. Okay? So, if we wanted to remove the entire positive or negative half cycle, then this is already considered as a clipper. But what if we wanted to remove a portion only of the negative half and not the entire negative half? Or what if we wanted to remove a portion of the positive half but not all the positive half? What are we going to do? Sometimes, okay, we place a DC source. So, class, this is already a combination of two inputs. So, what are the two inputs that we have? We have your AC input here, which is alternating in values, alternating in amplitude, changing in amplitude, and at the same time, sometimes it is positive halves and sometimes it is negative half. And we also have here a DC source. So, this is DC source is constant. That means with respect to time, it is not changing. So, we must analyze now your two sources. Okay, so what will be the effect if these two sources joins together or functions together? How will it affect your diode circuit here? So, this is an example of a series clipper with a DC supply. Okay, so do not memorize our step. You need to understand the steps but and not memorize it. Why? Because if you memorize it and then it happens that your quiz or sit work, for example, reverses this, so it becomes minus and plus already. So you will be you will not know what will happen if you just memorize the steps. So you might be confused. What if this is already reversed? Okay, so minus or plus first. So you have to understand our solution for this is unique, because once this circuit is changed, for example, what happens if this diode is reversed? Okay, so was reversed, for example, cathode first before anode, so technically your approach will be different. So what you're going to do is you have to analyze why did our solution is like that. Okay, so that even though we change the polarity of your source and we change the position of your diode, you know what to do. Okay, so this is a series clipper with a DC supply. So what are we going to do? First is you have to make a mental sketch, okay, of the response of the network based on the direction of the diode and the applied voltage level. So, for example, let us first analyze the diode using this source, okay. For example, we do not know this yet. We do not consider yet your AC source. Let us just consider your DC source. What will happen to the diode when we apply this DC source? Automatically, using the DC voltage V, okay? So, when you are analyzing only the DC source, okay? So, just the VDC, your V, the negative terminal is connected across your anode. So, when negative is connected at the anode, so what happens? So, that will make your diode what? Reverse bias. So, the DC source alone can make your what? Can make your diode reverse biased. Okay, now let us consider now the AC source. Okay, so let us consider the AC source. So for example, let us neglect first your V here. Okay, so let us consider the AC source. So considering the AC source alone, okay, so AC source, we have three conditions for the AC source. So what are your conditions? When your AC is 0, okay, when your AC is positive peak, okay, and when your AC is negative peak. What happens? Okay, what happens when we have these three conditions? Okay, when your AC is equal to 0, therefore your diode will not be biased. Why? Because you don't have any source. Let us say considering this, we do not yet consider this one. So if it is 0, it will not forward bias your diode. Okay, because you don't have any source. And 0 is lesser than zero point 0.7 if it is silicon, or zero point 0.3 if it is germanium. Okay. However, if we have here your positive peak, okay, so positive peak, imagine you have plus and minus here. So that means that if you have a positive peak, you are forward biasing your diode. So your diode is forward biased. Why? Because your positive is connected at your anode and your negative is connected at the ground. So therefore, you are forward biasing your diode. How about negative peak? So this is the negative peak. So imagine, okay? So imagine we still have more values in the middle. Okay, but we're just going to consider those 3 points first. So the peak positive and the peak negative, and of course your zero. So zero, zero, this is no current. Okay, so technically, because you have no source voltage, so therefore you don't have any current flowing, so this is considered as not operating circuit or reverse bias circuit. And then finally, we have negative peak. So if you have negative peak, so it means that negative is connected across your anode. Okay, here. So when the negative terminal is connected across your anode, therefore, we can say that at negative peak of your AC signal, your diode is reverse biased. Okay, so using the DC source alone, your diode is reverse biased. Using the AC source, it depends. During the positive half, or the positive cycles, your diode can be forward biased, and during the negative, your diode can be reverse biased. Okay, now, it doesn't happen that it is DC alone or it is AC alone. So sometimes, all the time, they go together. So once you turned on your circuit, it is consist of the positive half and of the negative half. So what do we do? Okay, so we say that if they are together, okay, so if your AC source is 0, therefore, we can say that your diode is reverse biased. Why? Because of the DC source. This is reverse biasing your diode. When your diode is in the negative peak, your circuit is also reversed. Okay, so why your circuit is reversed? Because the DC source is reverse biasing it, the AC source is likewise reverse biasing it, so therefore, during the negative half cycle, automatically, it is reverse biased. Now, what happens at positive half? So it depends. Okay? Since this is changing, since your input is changing, there is a time that your input is greater than this V here, and there is a time that your input is lower than your V here. So if it happens that your input is greater than your voltage V here, so that is the time that your diode is in the forward bias. But if your voltage here is less than your voltage V here, then your diode is in the reverse bias. So when will your diode be forward biased? Only during positive half, and when your voltage here is greater than your voltage V here. Because your voltage V here reverse biases your diode, and at the same time, your negative signal here also likewise reverse biases your diode. So that's the mental sketch, no? So first, analyze it. What will happen if it is the DC alone? What will happen if it is the AC alone? And what will happen if we combine the DC and the AC. Okay? So, we are going to determine the applied voltage. Okay, so what is the applied voltage? The applied voltage is your AC source because you're applying that to your circuit and it is changing, okay, from zero up to the positive peak, and then up down to zero again, and then down to the negative peak, up to zero again, and so on. So what portion or what value of the applied voltage we will be calling the transition voltage, okay? Transition voltage that will cause a change in the state for the diode. So what do we mean by transition? Change in state of the diode. Okay, so like this class, this is the moment that when your diode is in the on state, upon passing through the transition voltage, okay, it will be turned off. So that is the transition voltage. And if your diode is in the off state, upon passing through that input voltage, okay, your diode will be turned on. So, that is the change in state of your diode. Okay, so how do we determine that? How do we determine that? So, we just, this is your plus and minus VI, okay? And then we consider that your diode is shorted or forward biased. Okay, so if it is forward biased, and considering this as an ideal diode, we place here point 0 volts. Okay, so once the diode is shorted, its voltage is equivalent to 0 volts, not considering if it is silicon or germanium. Okay, but if it is silicon or germanium, we just have to place zero point 0.7 there and zero point 0.3. Okay, but this time we're just going to consider it to be an ideal diode. So let us say 0. Okay, and then this is the special portion of that transition. We know that if your diode is on, automatically there is a current flowing. Okay? But during this transition voltage class, this is a moment, this is a period wherein your VD is equal to 0 and likewise your ID is equal to 0 also. So, transition voltage occurs when your diode voltage is 0, at the same time, your current is also equal to 0. So, if your current is equal to 0, no current will flow across your R. So, what happens? Therefore, we don't have any voltage drop here. No voltage drop here because ID is equal to 0 and voltage is equal to I times R if I is equal to 0. So therefore, this is 0 volts. So what happens? We compute for the transition voltage. Okay, so how do you compute for the transition voltage? We just have to make a loop here. Okay, so you have there positive VI, then we have here minus V. Okay? Since this is 0, this is also 0, so this is equal to 0. So, what is your input voltage that will change the state of your diode? Okay, so when your VI is equal to V. So, this class is your transition voltage. So, this will change if the source is interchanged or the diode placement is interchanged. So, this transition voltage is good only for this example. Okay? So, we have here your transition voltage, which is VI minus V is equal to, VI is equal to V. Okay? And then, be continually aware of the defined terminals and polarity of VO. Okay? So, once your diode is in the on state, okay? So, once your diode is in the on state, what happens? So, you have your voltage here with you, and then this is shorted, and then there's a current already flowing across R. All you have to do is to have your KVL here. Okay? So, when your diode is in the on state, we have here your VI plus, so this is plus VI. You have minus V. You have here minus VO is equal to 0. So what is VO? VO is always equal to VI minus V. That is during the time that your diode is in the on state. Okay? Now, what happens when your diode, so this is on the on state. So what happens when your diode is in the off state? So when your diode is in the off state, this is open, right? And if this is open, no current will flow across your R. So therefore, since VO is in parallel with your R, your V out is equal to 0. So always remember, class, in a series clipper configuration, once your diode is in the reverse bias mode or in the off state, automatically our output is equal to 0. Okay, what's next? It can be helpful to sketch the input signal above the output and determine the output at an instantaneous value of the input. Okay, so what do we have here? So we can go back at this transition voltage. Let us analyze again. Okay, using this transition voltage. So we have here when your VI is equal to V, okay, this is short transition voltage every time that your VI is equal to V. That is your transition voltage. What will happen when your VI is greater than V? Okay? And when your VI is less than V. So when your VI is equal to is greater than V, that means your diode is in the forward biased mode. And if that is in the forward bias mode, our output will be equal to VI minus V. So since VI is greater than your V. Okay. Now, what if your VI is less than V? When our VI is less than V, a while ago we have analyzed that, okay? Because since V will reverse bias your diode, and since your VI, if it is lesser than your V, so that means it is negative, okay? So that will further reverse bias your diode. So therefore, this is reverse bias. So every time your VI is less than V, okay, our output is equal to 0. So you only need these three, okay? So you only need these three, class. The transition voltage, because every time you reach VI is equal to V, when your diode is on, it will become off. When your diode is off, it will become on. When your VI is greater than V, your output is equivalent to VI minus V. And when your VI is less than V, your VO is equal to 0. These three, okay, will help us sketch our output waveform. So it says here it can be helpful to sketch the input signal above the output and determine the output at an instantaneous value of the input. So let us do that. Okay, let us do that, class. This is my input. Okay, so this is my input and this is my output. Okay? So this is my VI, my positive VI, and this is my negative VI. What is the representation for V? V is a DC source, right? So since V is a DC source, and so we have to place that, okay? We have to place that as a DC source, like that. Okay? So that is a DC source. So this is your V. Okay? So these points here, 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 and here. So these are the points of transition. So what do we mean by points of transition? Because during these points, from on state, your diode will become off, and from off, your diode will become on. Okay? So if we project that downward, these are our transition voltage. Okay. So, These values here from 0 to V, these are V which are less than your transition voltage. Remember, when VI is equal to V, so this is transition. When VI is greater than V, you have your on. VI is less than V, this is off. Okay, so this value here, this small portion here, is when your VI is less than V, right? Because it is lower in value. So that means your diode here is in the off state, like this. So we will start with 0. Now, what happens next? All of the answers here, all of the values here falls under this. VI is greater than V because all of your voltages here are greater to whatever value of voltage here. So in this case, we have an output. So therefore, we can place your output here. But if this is peak value, if this is peak value, okay, this is no longer peak value. Why? Because it says that our output is equal to VI minus a certain V. So this is a somewhat lower value which is equivalent to VP minus V. And then we have a transition. So what do we mean by transition? Initially, our diode here is on. So, upon reaching transition, it will be turned off. Why? Because all of these values now are lower than V. So, we are here again. And what happens is from here to here, your output is equal to 0. Because every time your VI is less than V, your output is equal to 0. And then, we reach transition again. So, what do we mean by transition? From off now, your diode will also be turned on with a value which is also VP minus V. And then transition again, so this is also equal to 0. So you might be wondering, Ma'am, that is also a half wave. So it looks like a half wave. But really, we didn't remove just the negative half. Why? Because we removed the negative half, okay? So we removed the entire negative half. This was removed. And not only that, we also removed everything that was less than your V. So this was also removed. So we didn't just remove the the negative half, we also removed a portion of the positive half. So what is the assurance that we removed a portion of your positive half? Because if this is VP, the peak voltage here is no longer VP, but this is already VP minus V. So always remember, class, in a clipper circuit, when we get the peak to peak voltage of this, if we get the peak-to-peak voltage of this, it is always lesser than the peak-to-peak voltage here because this is already what is left, okay? Which is equivalent to VP minus V. So, since this is lesser than this one, we have a clipper circuit. That means a portion of our signal was removed. Okay? So that's it. So first, you make a mental sketch, and then you get the transition voltage, and then analyze the transition voltage, determine what will happen during the forward, what will be the output, and during the reverse it will be 0, and then you sketch your output signal. So the output signal here is always in a form of a waveform also. Okay, so it will be the one which what portion of your input signal will be removed. How about this? So let's have an example. Okay, so let's have an example. We have here determine the output waveform. So our input is 20 volts. So this is 20 volts peak. And this is our circuit. Okay? So analyzing the circuit, see, we have interchanged this one. Okay? So if we're going to analyze the source only. Okay? So if we're going to analyze The source only. Okay, so the DC only. If you're going to analyze DC only, what do you have? So if it is DC only, you can see that your 5 volts here, okay, your 5 volts here is connected across your anode. See? So since 5 here is connected to this, that means your diode is forward biased. Okay? So how about AC only? How about AC only, class? So during positive half, this is plus and minus. So 20, it is connected here at the anode. So during the positive half, your diode is also forward biased. How about during the negative half? During the negative half, since this is minus and plus, minus is connected to your anode, so this will reverse bias your diode during the negative half. What if we combine them together? Okay, so if we combine them, even though your input is equal to 0, still your diode is forward biased. Why? Because of the 5 volts here, which will forward bias your diode. Okay, now, during positive half, this is forward, and this is also forward. So, during positive half, we can say that this is really in forward bias mode. During negative half, okay, so this can be reversed. But if the value of your voltage is less than 5 volts, because if the value of your voltage here is greater than is more than 5 is less than 5 volts, therefore 5 volts can still forward bias your diode. So to know that, we need to solve for the transition voltage. So how do we solve for the transition voltage again, class? So to solve for the transition voltage, okay, so we're going to determine, so this is minus plus, this is 5 volts, right? So this is your input. What is your input? What is your transition voltage? So your diode is equal to 0. At the same time, your ID is equal to 0. Therefore, the voltage drop across your R is also equal to 0. Okay? So this is the transition voltage. How to solve for the transition voltage. So if we're going to make a KVL here, so we have there positive VI. Okay? So you have plus 5. This is 0, plus and minus. So minus 0 is equal to 0. So what is your transition voltage there? Our transition voltage is equal to negative 5 volts. Okay. So, negative 5 volts is our transition voltage. So, what do we mean by that? Okay. What happens when your VI is greater than negative 5 volts? And what happens when your VI is less than negative 5 volts? So, what are the voltages that are greater than 5 negative 5 volts? So those are your positive half cycle. And during your positive half cycle, automatically our diode is in the forward bias mode. So every time that your VI is greater than 5 volts, so that is negative 4, negative 3, or even 0. 0 is greater than negative 5. 1, 2, 3 until up to 20. So those are greater than negative 5. So in this case, we can say that your diode is in the on state. And when your input is lesser than negative 5, so what are those inputs that are lesser than negative 5? So you have negative 6, you have negative 7, up to negative 20, and so on. So your diode is in the off state. And what happens when your VI is exactly equal to negative 5? So that means you are in a transition voltage. Okay. So, when your diode is in the on state, what do we do? So, when your diode is in the on state, So during the on state, we compute. Okay? We compute again. So what do we have? We have VI, okay? And then you have what's our form, what's our ano? So you have there VI, and then you have plus 5. So this time we have your VO. So minus VO is equal to 0. So every time your diode is in the on state, your output voltage is always equal to VI plus 5. Okay. And every time that your diode is in the off state, since that is series, your VO is equal to 0. So we just need this. We just need this, and then we need that your transition voltage is equal to negative 5. Okay? And then when your VI is greater than negative 5, your diode is in the on state. When your VI is less than negative 5, your diode is in the off state. So once we know this, okay, we can easily solve or we can draw the output waveform. So how do you draw the output waveform? So this is our input. This is our input. So this is 20. This is negative 20. And where is your transition voltage class? It is negative 5. So, that is a straight line. That is DC. So, where do we place that? So, this is negative 5. So, this is your negative 5 volts. Okay. Let's have a sketch. So, when will your input be equal to negative 5? So, those are the transition voltages. So, this one, this one, and this one. Okay, so let us project that. Okay, like that. So, what are these values? These are 0 to negative 4. So, 0 to negative 4, these are your output when these are your input that is greater than negative 5. These are the times when your diode is in the on state. So during these times, okay, what is your output? So when your diode is in the on state, our output is VI plus 5. So let us take, for example, when your input is equal to 0, your output is 0 plus 5. So therefore, I will not start here. I will start here. Okay? And then, when my input is 20, my output is 25. So why 25? Because it is 20 plus 5, right? So when my input is 4, for example, 0, when my input is negative 1 here, it is negative 1 plus 5. So my output is still 4. Until I reach the transition which is equal to 0. So what is the transition? My transition is when negative 5. So when my input is negative 5, so I have here negative 5 plus 5, that is the time that I will be here at 0. And from here to here, my output, all of the values here are negative 6 up to negative 20. All of them, those are VI, which is lesser than negative 5. And when it is off, my output is equal to 0. So from here to here, my output is equal to 0. Upon reaching transition, it will again increase up to 25 again. And then at transition, it is 0 again. Up to transition. Like that. So this is now my output. Okay, so if you say, oh, it's just like a half-wave rectifier because the entire negative half cycle was removed. No, we didn't remove the entire negative half cycle. What did we remove? We only remove those values that are less than negative 5. And where is that? These values. We only remove these values. Okay, so what happens to this value is we just added that upward. That's why instead of 20 here, we have here 25. So that if you're going to make use of this one, the peak to peak value here is this is 20 and 20. the peak to peak is 40. Okay? So if we're going to get the peak to peak voltage here, the peak to peak voltage here is 25. So we didn't remove the entire, because if we're going to remove the entire negative half, it should be 20 also. But we have here 25. So that means we just removed 15. And what is that 15? Those that are below negative 25 volts. So that is how your clipper is being analyzed. So you just get the transition voltage and then analyze what happens when your input is greater than or less than the transition voltage. And if the diode is on, what is your output? And when the diode is off, automatically your output is equal to 0. So this is how you're going to sketch your output waveform. Okay? So, it is much easier, class, if we have a square wave, because the difference between a sinusoidal and a square wave is an AC signal, but it has only two values. So, during the positive half, the value is 20, and during the negative half, the value is negative 10. Okay? So, we can easily analyze them just one by one. Okay? So, we can analyze them just separately. Okay, so how do you do that? So for example, during the time, okay, of positive half cycle, okay, is equivalent to when your input is equal to 20 volts. Okay? So, when your VI is equal to 20 volts. So, let us analyze. So, if our VI is equal to 25, so we have here plus, so this is minus plus. So, this is your diode. This is your output. Okay. And then I will be placing here plus and minus 20. Okay, and then I have here your 5 volts. And then I will measure here your output voltage. So by having a loop here, I have here plus 20, plus 5, plus and minus. So minus VO is equal to 0. So during positive half cycle, okay, so VO is equal to 25 volts. So this is my output during the positive half. Okay. What if my input is equal to, negative 10? Okay. So what happened when my input is equal to negative 10? Okay. So we said earlier that negative 10 is lesser than negative 5. Okay, so if negative 10 is lesser than negative 5, therefore, we are going to reverse bias your diode. If that is reverse bias, so no current will pass through that. Okay, so look, the voltage being implemented here is like this one, which is not in the same direction with your diode. So therefore, this is in the reverse bias mode. Okay, so what is your output? Your output is equal to 0 since this is open. Always remember that once your diode is in reverse bias mode, automatically for series diode configuration, it is equal to 0. Okay? So finally, we can draw the output waveform. So how do you draw the output waveform? So you have to draw, okay? So our input is like this. So this is 25 and this is 10. This is 25 and this is 10. This is your input. So let us now draw the output. At 25, okay, our output is at 25, at 20 volts, our output is 25. At 10 volts, negative 10 volts, our output is 0. So if we're going to redraw that, this is our input. So this is 20 and this is negative 10. During positive half, our output is 25. During the negative half, our output is 0. And then 25 again, and then 0 again. Okay? So you might say that we just remove all the negative half. No, we didn't remove all the negative half. We just remove a portion of the negative half. Okay? So how do we do that? How do we know that? If we're going to get the peak to peak value for this is equal to 30 volts peak to peak. If we're going to get the peak to peak value for this is equal to 25 volts peak to peak. So that means only 5 volts was removed. And where is that 5 volts? So we remove just a portion of this negative half cycle. So we just remove a portion of that half cycle. So the remaining 5, we just move it upward. So this is an example of a negative clipper. So why is this a negative clipper? Because a portion of the negative half cycle was removed. So when the portion of the negative half cycle was removed, we call that a negative clipper. But when a portion of the positive half was removed, that is your positive clipper. So this is the difference between a square wave and a sinusoidal wave. So for square wave, you can analyze directly the positive and the negative half cycle because anyway, there are just two values. Okay? So next is a parallel clipper. So this is an example of a parallel clipper. So your diode is in parallel with the load. Okay, so this is your output waveform. So if you're going to consider this one, okay, considering this circuit here, what happens during positive half and during negative half? Okay, so let us see. For example, this is your input. This is my input. And this is my diode clipper. Okay. So during positive half cycle, that will be plus and minus. Okay? So positive is connected to the anode and negative connected to the cathode. So this is forward biased, right? So what happens when your diode is in forward bias? So when your diode is in the forward bias mode, it is shorted. The voltage across this is equal to 0. So since your output voltage is in parallel with this short circuit, during the positive half cycle, your output is equal to 0. Like that. Okay? So that is what happens. Now, we have here minus and plus during the negative half cycle. So what happens during the negative half cycle? So during the negative half cycle, your diode, your negative is connected across your anode. So therefore, this is open. So this is open. And if this is your VO, okay, this is plus and minus, and this is minus plus. So what you see is just the input, but in the reverse manner. Since this is minus and plus, this is plus and minus. So during the negative half cycle, so this is for parallel. Okay? So for parallel, if it is forward bias, your output is 0. But if it is reverse bias, we have an output. And what is your output? Your output is equal to the negative of your input. So why negative of your input? Because you have here, this is minus and plus, and this is plus and minus. So if we're going to redraw it here, okay, so you have negative your input. So that means if we have here your positive half, so this is equal to 0, and then negative, that is your output. So this is your, that you can see in the output side. Okay, so in this case, this is a positive clipper. Why? Because a portion of the positive half cycle was being removed. Okay. But what will happen if we do not want to remove all the positive or all the negative, just a portion? What we do is we add a DC source in this case. So in this case, we have a DC source which is negative, uh, which is 4 volts. And then we have a triangular wave. So this is one example. So we have here a triangular wave with a positive peak of 16 and a negative peak of negative 16. Okay, so what do we do here? We analyze. Okay, so how do you analyze that? Okay, so let's analyze that, class. Okay, so without considering your input signal, without considering your 16 here, plus and minus 16 here, what will be the effect of your 4 volts across your diode? So the DC source alone, this will make your diode equal to what? Forward bias. Okay? So the DC source alone, DC alone, this will be forward biasing your diode. Okay. How about AC alone? Okay? So, plus 16 volts, okay, the peak voltage plus 16 volts, what will happen to your diode? If we have here plus and this is negative, so that will be what? Reversing your diode. So, at positive peak, this will be reverse biasing your diode. Negative peak, so that is minus here and plus here, that is forward biasing your diode. Okay. So we join them together. What will happen if we join them together? So since your DC source is forward biasing your diode and your negative 16 is forward biasing also your diode. So during the negative half cycle, we know that your diode is in the forward bias mode. But during the positive half cycle, there is a time that your diode will be on and your diode will be off. So how do we know? We get the transition voltage. So how do you solve for the transition voltage? So for the transition voltage, okay, let us redraw the circuit. Okay. So this is the time when your VD is equal to 0 and your ID here is equal to 0. So what is your VI when your VD is equal to 0 and your ID is equal to 0? So let us make a loop. So we have here plus VI. We have here, this is 4 volts, right? So we have here minus 4 is equal to 0. So VI, which is equal to 4 volts, this is our transition voltage. Okay? So this is our transition voltage. So what happens? When your VI is greater than 4 volts, what happens? When your VI is lesser than 4 volts, what happens? Okay, so when your VI is greater than 4 volts, so that means 5 to 16, your diode is reversed biased. Okay? And when your diode is less than 4 volts, so that means 3 downwards, your diode is forward biased. Okay? And what happens when your VI is exactly equal to 4 volts? That is your transition voltage. So transition voltage again, when your diode is on, it will be turned on. And when your diode is off, it will be, when your diode is on, it will be turned off. And when it is off, it will be turned on. So we just need this two. Okay? And then, the output. When your diode is forward biased, what is your output? Okay? So when your diode is forward biased, this means that your diode is shorted. So what is your output? Your output is in parallel with this branch. So when your diode is forward biased, what is your output equal to? So since this is shorted, your output is equal to 4 volts. So during your diode is forward bias. And when is that? All that is lesser than um all that is lesser than 4 volts. Okay? So when your diode is reverse biased, what happens? This is open. So when this is open, the effect of 4 volts is no longer there. So therefore, whatever your input here is your output. So therefore, your VO is equal to your input, like this one. So when forward biased, your output is 4. When reverse biased, your output is equal to your input. So just this, okay? Just remember these values. We can draw your circuit or your output. Okay, so how do you draw your output? Again, it is said that you draw your output below your input. So this is our input. So this is 16 and this is negative 16. And then we have your DC, which is 4. So this is your DC. Okay, so where are your transition voltage? When your VI is equal to 4 volts. So this one, this one, this one, and this one. So let us project. Okay. So what are these inputs? These are those lower than 4 volts. Okay. What happens when your diode is lowered, when your input is lower than 4 volts? So when your input is lower than 4 volts, okay, you are forward biased. And what is our output if you are forward biased? Our output is 4 volts. So we draw. So this is 4 volts. Okay. And then transition. From on, your diode will be off. Okay? From on, your diode will be off because it will become 5, 6 up to 16. And then VI is greater than 4. So it will be reversed. And when it is reversed, your VO is equal to VI. So what is our VI? This is our VI. So our VO will be equal to your VI. So if this is 16, this is also 16. Transition again. So upon reaching transition, those are those lower than 4. And if it is lower than 4, it is reversed. So the output is, it is forward. So the output is 4. So from here to here, your output is 4. And then transition again, it will be reversed. The output is 16. Right here. And so on. So we remove a portion of the negative half and some of the positive half. So this is still considered as negative clipper because majority of the waveform that we remove is from the negative half. Okay? So as you can see, the peak to peak voltage here is 32, while in this case it is only 16 volts. So what are those removed? So this whole entire negative 16 plus your 4 here. So those are the things that was removed. Oh, no, no, this is 60, this is 4. So this is only 12. So this is only 12 volts. So we remove a portion, the whole negative half, and a portion of your positive half. Thus, this is how a parallel clipper functions. Okay? So there are different circuits. So don't try memorizing them. Okay? So do not memorize the formula. So you have to determine how did we manage to solve for it. Like for example, for this configuration, we solve for something like this. Okay, so look at the output. It's VO minus V. So that is what we had in our previous. And this is our example a while ago. So we have here VM plus V. Okay, so these are the different possible combinations for your positive and negative series clippers. And this is for the positive and negative parallel clippers. So in our previous example, it is like this one, like this one. I wear this one. Okay, so look at the output. It looks like this one. Okay? So do not memorize. You have to analyze it properly. Okay? So application, the next application is a clumper circuit. So, what is the difference between a clipper and a clumper circuit? So, like a clump, okay, you will not be removing anything. So, we will not remove anything because if we remove anything, that is already a clipper. So, what we do is we just add a DC level to your AC voltage. It's either you just put it upward or downwards. You just change the DC level below or above your DC 0 point. Okay, so another name for clumper circuits are DC restorers. Okay, so they add a DC level to an AC voltage, but they do not clip off. They do not remove. Okay, so technically, it is composed of a capacitor, a diode, and a resistive element. So we now have a new component here in a form of a capacitor. Okay? So your DC supply for an additional shift can be added. So the capacitor will fully charge or discharge in 5 time constants. So the total swing of the output is equal to the swing of the input signal. Okay, so if we're going to consider this example, unlike clippers, we can start right away. So in clumpers class, we have a step. So we have an actual steps to follow. So unlike clipper, you just analyze, you just sketch. So in this case, in DC, in clumper circuits, we really have a particular steps to follow. Okay? So while following the steps, let us do this example. So for example, I have here your V. So this is V and this is negative V and this is our circuit. This is your capacitor and this is your diode. Okay, and this is your resistor. This is your output. Okay. So this is your C and this is your diode and this is our input. Let us follow the steps. Okay? So what are the steps? Number 1, we always start, okay, will start the analysis of clumping networks by considering that part of the input signal that will forward bias the diode. So we need to start where your diode will be forward biased. Okay, so unlike in clippers, even though your diode is reverse biased, we can always start anywhere. Okay, in the analysis. Here, we really have to start. So for example, during positive half, we have here plus and minus. This is V. Okay, so will this make your diode forward bias? So if yes, we can start right away. But if this can make your diode reverse bias, so we have to remove. Okay, we have to go to the other half cycle. But since in this our example, during the positive half, your diode is right away forward bias, then we can start. Okay, so we have to start the analysis of clumping networks by considering that part of the input signal that will forward bias the diode. During the positive half cycle here, plus, and then this is anode, so it will be forward bias, then we can start during the positive half. Okay, so during the period, so let us say positive half, your diode is on. So we can start. Okay, so your diode is on, so we can start. And then, following the steps, During the period that the diode is in the on state, assume that the capacitor will charge up instantaneously to a voltage level determined by the network. Okay, let us analyze. So let us analyze. When your diode is on, so therefore this is what? Shorted, right? So this is shorted. So since this is shorted and this is in parallel with your resistor, and that is in parallel with your VO, we can say that your VO is equal to 0 here. Because this is shorted and this is in parallel, so what is the voltage across this one? So this is equal to 0. So therefore, your VO here is equal to 0. But the important thing to consider here is when your diode is shorted, your capacitor is charging. Okay, how much is your capacitor charging? So your capacitor is charging, we have here plus V. So if we have here your input, so let's have a loop. So we have here plus, minus, negative to positive. So you have here plus V. You have plus V, you have minus. Let us call that VC. So this is 0 is equal to 0. So your VC is charging up to V. Okay? So, during the period that the diode is in the on state, assume that the capacitor will charge up instantaneously to a voltage level determined by the network. So, this capacitor is charged up to voltage V. Okay? So, assume that during the period when the diode is in the off state, that the capacitor will hold on to its established voltage level. So, during the negative half cycle, during the negative half cycle now, so this is minus plus, it is assumed that we have here your minus plus VC. So your charge, your capacitor will hold on to its original charge, which is equivalent to V. Since this is already reverse bias, your diode here is open. So since your diode here is open, this is no longer equal to 0. So this is open, where will your voltage charge going to? So you will be having a loop outside. And this time we have here minus and plus V. So if we're going to have your loop there, you have here minus V, negative half. You have here minus VC. You have here minus VO is equal to 0. So what is your VO equal to? But VC is equal to V. So we can rewrite this as minus V minus V minus VO is equal to 0. So what is VO? VO is negative 2V. So during the time that the diode is in the on state, our output is 0, but your capacitor is charging up to V. And then, when your diode is in the negative half cycle, your capacitor will hold on to its charged voltage, which is equivalent to V. And then, having a loop, we have an output which is equivalent to negative 2 volts. Okay, so what happens? Throughout the analysis, maintain the continual awareness of the location and reference polarity for VO to ensure that the proper levels for VO are obtained. So during positive half, your VO is equal to 0, and during negative half, your VO is equal to negative 2. Keep in mind the general rule. So we have a general rule that the total swing of the output must match the swing of the input signal. Remember, we're not clippers. Okay? So therefore, the total swing, the peak to peak of the input must be equal to the peak to peak of your output. So this is our input. This is our input. This is V, and this is negative V. So if we're going to get the output of the peak to peak of that, this is equivalent to 2V. Okay? So what's your input and output? What's your output? During the positive half, what is our output? Our output is 0. During the negative half, what is our output? Our output is negative 2. So if we're going to get the peak to peak of this, This is also equal to 2 volts. See, no signal was removed. No signal was clipped off. We just lowered down. We just lowered down the DC level. And that means this is a negative clumper. So why this is the negative clumper? Because we lowered your DC level below your 0 point. So this is an example of a clumper. Okay, so in this case, we just have to follow the steps. Okay, so let's have another example. Determine VO for the network given. So before we start, so this is our example. What do we mean by this? Okay, so we just have to make sure that your circuit is properly functioning. So how do we know that your circuit is properly functioning? We need to know the time constant. Okay, so the time constant, this is another term. So this is another term class, okay? So time constant is given by this one. So this is a time constant. And this is given by your RC network. This is the time that your capacitor will be fully charged or discharged. Okay? So it is said that to be fully charged and discharged, you need up to 5 time constants. So you just have to multiply this by 5. Okay. So in this example, what is the time required for our capacitor to fully charge and discharge? Okay? So our time constant there is equal to, this is 1, our R is 100 kilo ohms multiplied by 1 microfarad. Okay? So our time constant is equivalent to 100 kilo ohms times 1 microfarad. So micro means -6, kilo means +3 exponent. Okay? So that will give you 100 milliseconds. So to fully charge and discharge, we need 5 time constants. So that will give you 500 milliseconds. What do you mean by that? So we need 500 milliseconds once to fully charge your capacitor. And you also need 500 milliseconds to fully discharge it. So we have to make sure that during the time that your diode is not conducting, your capacitor is not easily or does not discharge very, very fast. Okay? So we need to determine your input. Our input here is 1000 hertz. So what do we mean by 1000 hertz? So frequency is 1 all over period. Okay. So if our period is 1 all over f, so 1 all over 1000, so that will give us 1 millisecond. Okay, so that means you have 1 millisecond to complete a cycle. So 1 millisecond positive half, 1 millisecond negative half. So after your capacitors is fully charged, it will be discharged after 500 milliseconds. And if our signal is 1 millisecond only and it will go positive again, we are not going to worry that your capacitor will be discharged during the entire duration. So the proper way is this must be longer than this one, because if this is shorter than this one, during the time that your diode is non-conducting, there is a possibility that your capacitor will be fully discharged, and we do not want that. So the proper design class is this is always greater than this one. So in this case, this is okay. Okay, so this is acceptable. What is not acceptable is if this one um is greater than this one, because it will be very, very long time again before the capacitor starts charging. So there will be a time that it will be discharged very, very fast. Okay, so using this problem, we determine what type of clumper circuit is this. We determine the output. And the output, when you say determine the output, it is a waveform. Because if this is your input waveform, what is your output waveform? So usually, in clippers and clumpers, the output is always in the form of a sketch. You have to sketch the output waveform. Okay? So, let's start. Step 1. What does it says in step 1? We start the analysis when the diode is in forward bias. Okay. So, by analyzing this one, during the time that your diode is plus positive, okay, positive half, we can say that this is plus and this is cathode. So in this case, this is reverse biased. So that is the time when we skip the positive half because we have to start always during the time that your diode is in the forward bias mode. And when will that happen? That will happen if this is minus and this is plus, and that is during the negative half cycle. So we will be starting at the negative half cycle. Okay? At the negative half cycle, your diode is in the on state. Okay. So when your diode is in the on state, what happens? This is shorted. Okay. So since this is shorted, what is our output? Our output is in parallel with this branch. This is parallel with the resistor and parallel with this branch. So in this case, if this is shorted, our output is equal to the source, which is 5 volts. If it has a value here of a diode, let us say silicon or germanium, you have to subtract zero point 0.7. Why subtract? Because this is minus plus and this is plus minus. They are not the same polarity. So therefore, we have to subtract. But since this is ideal, our output there is equal to 5. And during the time that this is on, your capacitor is charging. Okay, so how much your capacitor is charging? So if we're going to redraw that, this is minus plus. Okay, so during negative, so this is 20 volts. This is shorted. It's charging. And then we have here 5 volts. And this is your VC. So since this is minus plus, the direction is like this. So the polarity here is plus and minus. Okay? The polarity there is plus and minus. So we have here your loop. So what is your loop there? You have plus 20. You have plus 5. You have here your VC. You have minus VC is equal to 0. What is VC? VC is equal to 25 volts. Take note, this is VC. This is not the output. This is the charge of the capacitor once your diode is reverse biased. Okay? So it was the charge being dictated by your source. Now, during the positive half, what happened? Okay? So during the positive half, this is still minus plus VC. This is now open. So therefore, we don't have the effect of the 5 volts anymore. But we have here your R and we have here your output voltage plus minus VO like that. And this is plus minus. Okay, that is plus minus. What is our input source? This is plus minus 10 like this. So if we have a loop there outside, that will give us plus 10, okay, plus VC, but VC is 25. So plus 25 minus VO is equal to 0. So what is your VO? VO is 35 volts. Okay. Then we need to draw. Okay? We need to draw the output and the input. So, this is our input. So, this is 10. This is 10. And this is 20. This is 10. And this is 20. So, if we're going to get the peak-to-peak voltage of this, so this is 10 and this is 20, this is 30 volts peak-to-peak. Okay. So, during the time of positive half, our output is positive half, our output is 35. Negative half, our output is 5. Okay? So, positive half, this is 35. Negative half, this is 5. 35, this is 5. So, if this is 35 and this is 5, if we're going to get the peak to peak of this is also 30 volts peak to peak. Okay. We didn't remove anything. What did we do? We just place it above your DC level. So this is an example of a positive clumper. Why? Because we raised the value or we raised the DC voltage. Okay, so that's the difference between a clipper and a clumper circuit. Again, don't memorize, okay? Don't memorize because if we change the polarity of your source and then we change the position of your diode, everything will be changed. So, understand, analyze properly the circuit. Okay, so there are other, so it can also be a clumping network with a sinusoidal input. So you are just either raising it above, so it's a positive clumper, or below, it is a negative clumper. Okay, so we have here different clumping networks and circuits. So you can practice, okay, or you can have an practice problems within the book. Okay. So we have here an assignment. I will be placing another drop box for the assignment. We don't have a sit work, but we have an assignment. Okay. So the this is made up of rectifiers, clippers, and clumpers. Okay. So you have to do that, and you have to uh, submit your assignment in our school book Dropbox. Okay? So, thank you for listening again. So, that's the end of our video for clippers and clumpers. We still have one diode application, which is a regulator, and that will be the coverage of our next video. Again, thank you for listening and have a nice day. Okay, bye.